Hi everyone, I'm Nadine, one of the TAs for EECE 331. Welcome to today's problem-solving session focused on preparing for the upcoming midterm. And before starting, let me outline how we structure these sessions. So we'll be walking through several practice problems similar to what you might encounter on the midterm. For each problem, I'll first present the setup, then we'll walk through the solution step by step. Feel free to stop the video at any time to try to think about what you're doing or get the intuition behind it. Okay, so let's start by problem 1. In problem 1, they're defining a new type of graph called the tournament, which is a directed graph by definition that has two characteristics. It doesn't have a self-loops. For every two vertices in this graph, either U is pointing to V or V is pointing to U, not both, and one should exist. So we have a graph G equal VE that satisfies two properties, no self-loops, and either U till V, V till U, not both, and one should exist. Okay? So if we have like, let's say these nodes, and this one is connected, and node 1 is connected to node 2, then node 2 can be connected to node 1 by the other direction. By definition, it's either this or this. Okay? 1 is connected to 2, 1 should also be connected to 3. Between any two vertices, there is a connection. So let's say there's this connection. So if 1 is connected to 3 in this way, 3 can be connected to 1 in the other way. Okay? We also need a connection from 2 to 3. I'm saying إنه these kind of graphs ممنوع يكون في self. So such a node, such an edge is not right. Okay. To understand a bit من وين جاي هيدا definition, let's go to the real tournament where each node is a player 2, player 3, and let the arrow mean that the player at this end هو اللي عم يربح يعني speed at end B. Okay, so if player 1 ربح على player 2, then player 2 cannot beat player 1. Okay, it's self-contradictory. Okay, a player can't beat himself. No, it doesn't make sense. Okay, so we can't have self-loops. من هون جاية the definition of tournament. أو هون سمينا this kind of graphs tournament. They're asking us to prove إنه such graphs دايماً في بقلبهم a simple path. A simple path is a path that walks through all nodes, and it visits all nodes in the graph exactly once. So let's say عم امشي من player 1, then رحت عن player 2, then عن player 3. This is a simple path لأنه راحت عن each player وعند each player once, وما في loops بقلب هيدا الباث، وما في crossing، ما في node عم نقطع عليها more than one time. So it's a simple path. They're asking us to prove إنه each tournament عنده a simple path. If the tournament has n vertices, then عنده n-1, a path of length n-1, a simple path. Okay? The simple case that we can have إنه ما يكون عندي أصلاً connections. يعني my graph عبارة عن one node. This hypothesis إنه every tournament has a simple path, for every graph with just one vertex, whatever كان tournament أو لا, the claim إنه عنده a simple path is trivial لأنه أصلاً there is no paths, يعني there's only this node. So the simplest path that we have is of length 0, and the claim basically is trivial. So this is for the base case. when n equal 1. What you want to do is, for a graph of n vertices bigger than 2, okay? We want to prove إنه such graphs اللي هن tournament عندهم a simple path. Let's assume, for the sake of induction, إنه every tournament, let's assume every tournament having n-1 nodes عنده this simple path, has this simple path, okay? That visits all vertices exactly once. يعني عم نقول if this is a graph of n-1 nodes, a tournament graph, then I can find بهذا الجراف a path that goes over all nodes exactly once, okay? هذا الباث I will extract it بعدين و I will use it. طيب هذا my assumption. So what I want to do is to consider هلا the graph يلي أنا بدي consider n vertices. So consider a graph with n vertices. And if this is my graph of n vertices, let's try to reduce it to a graph of n-1 vertices to see what will happen with this with a simple path, okay? So let's pick any node in this graph, call it V, let's remove this node. طيب, we remove this node. What we created هلا is a graph J prime يلي بعده tournament. لأنه if I started by tournament ما فيني انزل البروبريتي اللي كانوا عندي اياهم. يعني let's say U was connected, U1 was connected to U2. أنا شلت a node V برا ما خاصة فيهم. Then U1 would still be connected to U2, okay? So ال characteristics اللي كان عندي اياهم بالدefinition بعضهم موجودين. إذا كل النودز ما كان عندهم self loops, by removing V ما حيصير في عندي self loop. So by reducing the graph, removing one node, حيضل a tournament, okay? It's a tournament, بس غير هيك هيدا was n node, so I removed one node, so it's an n-1 vertex tournament. وأنا I assumed by my induction hypothesis إنه every tournament of n-1 nodes عنده a simple path. So هيدا الشيء it has a simple path مثل هيدا الرسمة, okay? So let's take هيدا simple path يلي عندي إياها let's try نفهم شو عم بيصير فيها, okay? Let's hold be n-1 nodes يلي على path of the n-1 graph, okay? we have the node V. Okay, so نحن بالجراف J prime يلي هو عبارة عن J minus النود يلي شلناها, okay? إنه we have this simple path يلي فيها كل الnodes of J ما عدا V. So to create a simple path بالجراف J, we need to add على هيدا simple path only V. So basically all what we need to do is to figure out where to put V, okay? One can هيك يشوف trivial cases like what if V was connected to V1? If V was connected to V1, then put this connection يعني like let the path تمرق بهيدا الإدج وحتكفي ب a simple path ما حتنتزع my path وصار فيها all the edges, all the vertices of the graph G وبتقطع فيهم only once. So basically it's a trivial case where دغري we're done. Let's say we also let's say we don't have this connection, but instead we have another connection. Let's say this connection is from the other part. So let's say we don't have this connection, but let's look at the other case, the other trivial case. The endpoint Vn-1 is connected to V, okay? So if I have this case, it's also trivial to add only this edge. And by adding this edge, I will have a simple path that goes over all the nodes of G prime plus V. So I'm passing over all the nodes of G. In this way I created a simple path for the tournament T. Okay, so هول two cases are trivial, but let's say I don't have لا هيدي ولا هيدي. يعني let's say it's V1 the nodes Vn minus 1. Okay, let's say this is the node V, but I don't have this connection. I don't have this connection. Okay, let's think أول شيء about this one. Let's think about this one. If I don't have this connection, إذا ما في an arrow that's pointing from V till V1, by the definition of tournament, there should be an arrow that's pointing from V1 till V. Okay, so this arrow exists. Okay, and let's say I don't have also this connection. So by the definition of the tournament, I have the other direction. V is pointing to Vn minus 1. Using these two connections, I cannot really build my simple path. لأنه if I decided to add this one, then there would be two ways to go, and I would be crossing V1 twice, so it's not a simple path anymore. The same for the other part. If I choose this one to add, then I would be crossing Vn minus 1 two times. It's not a simple path anymore. Okay, so I need to find another place where to put my node V such that the simple path stays a simple path. Okay, at this point I will be claiming إنه there is this structure بقلب my path. Okay, such that أنا في عندي this path لهون. هيدي النود is connected to V in this way, و V is connected to this node in this way. Okay, وفي كملت الباث. إذا this thing exists عن جد, what I can do is simply removing هيدا الedge و adding instead had two edges. So let's look شو بيطلع لنا. بيطلع لنا this simple path. Okay, which is going هيك بعدين هيك then هيك then هيك. Okay, so if I can prove إنه such a thing exists, basically I'm saying إنه okay, I can build the simple path easy by removing this edge here and adding these two edges. To be able to prove such a thing, let's try to find this node. Okay, and particularly let's try to find the first node. Let's try to find the first node in the path يلي عندها property. يعني let's try the first node Vi such that V is pointing to Vi. Okay, if hidden node is the first node such that V is pointing to Vi, معناتها V cannot be pointing هيك كمان على Vi minus 1. وإلا كانت هيدي طلعت Vi. لأن أنا I'm taking the minimal. No. If هيدي the minimal, then هيدي إذا ما فيها تكون الكاركترستيك كمان موجودة على النود اللي قبلها. So عم أقول عندي نود Vi كتير هون نودز بالباث. وهيدي النود Vi هيدي أول نود في عندي هاي الكونكشن من V. يعني هيدي ما عندها هالكونكشن. أوكي؟ بس look, this node belongs to G, this node belongs to G. By the definition of G that is a tournament, there should be a connection between V and Vi minus 1. If not in this direction, then the other direction. And well, can you see the path? Well, if you look, I did prove that by finding the minimal Vi that is connected in a way V is pointing to Vi. Vi is يعني دايما I can find such a Vi لأنه V is connected to Vn minus 1. يعني this node can be the minimal one. But I'm trying to find the minimal. If there is something smaller than Vn minus 1, I take it. Okay. I proved if Vi is connected to Vi and Vi is the minimal one, then Vi minus 1 is connected to V. So صار عندي Vi minus 1 is connected to V is connected to Vi. Initially I had Vi minus 1 connected to Vi بقلب الباث. So كان في my path هون من V1 then ل Vn minus 1. So all what I need to do really is to break this وأعمل insertion ل V here. يعني all what I need to do is اجي لهون let me break this connection, let me insert هيدي ال connection instead. هو الشيء اللي عملناه هون و then I get my path that I want. وهيك بكون عملت a simple path in the tournament. So I just proved إنه for any tournament there is always a simple path that goes على كل ال vertices و exactly once على each one. Okay? So this is it for the first problem. Okay, let's solve now problem 2. Problem 2 is about DP applications. If you remember the subset sum problem, this one is a modification subset sum problem with an additional constraint. It's called the symmetric subsequence sum. If you remember the original problem, it was given an array A of elements. We need to find a subset S that belongs to A such that the sum of elements in S equal a target T. أكيد all positive. So the modification that we're adding now, the constraint that we're adding now, is that S should be symmetric. And what do we mean by a symmetric subsequence? Basically, if this is S, then the element and its mirror should be the same. So it's like I'm saying, put this subsequence in a string, then the string should be a palindrome. Let's take an example. So if I'm saying 1, 2, 3, 4, 5, this is obviously not symmetric at all because the element and its mirror, they're not equal. And if I look at this sequence like a string, then it's not a palindrome. But if I take this subsequence, then clearly it's a symmetric one, purely symmetric, because each element and its mirror, they're equal, they're the same. Okay, so it's the initial subset sum problem, but now with an additional constraint that the subset that I want to find should be symmetric. And to check if a subset is symmetric, basically I need to compare. I'm comparing the elements if they're equal or not. So from here comes the idea that we need 2 pointers this time and not one. Let's look at an array, and let's say I'm taking this part of the array, dp at ij, target t. What I'm trying to achieve is there a subsequence starting at I, ending at j, that can give me the sum t, the sum u. So looking at one slice of the array, starting at I, ending at j, I want to know if there a subsequence here that is both symmetric, and it sums to the target u. Okay, let's say this is the case. Then let's say these 2 elements are equal. I can say that I either take them, if they're equal, then taking them both won't affect my symmetric characteristic of S, or I don't take any one, I skip both. Either take them or I skip both. Okay, taking them or skipping both won't affect the solution, that the symmetric characteristic of S. because if something she is symmetric, I add an element home that are equal, then the result will be also symmetric. And if I don't add anything, then I'm still in the symmetric case. Okay? So let's say the two elements at the endpoints are equal, then I can either take them or I can skip both. But if they're not equal, like if A at I not equal to A at J, either I look at this part from the array, from the sub array, or I look at this part. So I either remove A at I or I remove A at J. And what I just said here is the recurrence relation that we want. dp at I, J, U. If AI equal to AJ, then what I can do is either take both or skip both. And by taking both, I mean dp at. If I took this element, رح أمشي one step لقدام, it's I plus 1. If I took this element, بمشي one step لورا, J minus 1. And my sum U is my sum كانت initially U, I've added two elements, A at I, A at J, اللي هن equal. I've added both, okay? So كأني I've added 2 times AI. So my remaining sum now is U minus 2 times AI. It's U minus 2 times AI, okay? This is the recurrence if I take both. It's or I skip both, which is dp at I plus 1 that I skip, J minus 1, or the sum بعدها the same. This is the recurrence relation if AI equal to AJ. Otherwise, if they're not equal, then either I cut my subsequence, my sub-array قبل J أو بعد I. So either I look at كل شيء excluding AI أو I look at كل شيء excluding AJ. So it's dp at I plus 1 J or dp I J minus 1. Okay? This will allow me to continue the algorithm as I don't find elements يلي هن not equal. هيدا my recurrence relation أكيد for I less than J. هلا for the other cases, let's look at the base case. For the base case, it's either عم أطلع ب empty sequence, I don't have anything, or I have only one element. إذا عم أطلع ب an empty subsequence, then I'm saying إنه J equal I minus 1 basically. Then B at I J U would be true if U equal لزيرو بس, لأنه the only sum that فيني أعملها from an empty subsequence is 0. Any other U تعطيني false. If I have one element, يعني I equal to J, then dp at I U. So basically عم أطلع ب only one element وعم أقول is this element equal to U, يعني taking this element معقول يطلع لي U. So basically it's true if AI equal U, false otherwise. Okay? So this is the recurrence relationship. Then the base case, you don't forget the base case in the exam. It's the most important thing to start filling up the table. It's basically where we start. And the time analysis, we're going over all I, over all J, over all U, from 1 till N, from 1 till N, from 1 till T. It's a 3D table. So it's basically an O of N times T, which is O of N squared times T time. But also an O times N squared T space. لأنه I will be building this table يعني فيها all I, all J, all U. Okay? So this is it for the second problem. Okay. For the third problem, it's again about graphs. It's about proofs. Okay, so بيقولوا لنا إنه we're looking now at specific classes of graphs, the bipartite graphs. And a bipartite graph is a non-directed graph. A non-directed graph such that the vertices تبعه can be divided into two subsets, V1 and V2. The graph is VE, such that every edge connects a vertex in V1 to one in V2. And there are no edges in the same set connecting two nodes in the same set. So if we look at this example, if I say this edge, I want to put it in V1, then I have this element connected to it, or this element connected to it. So هوتنين ما فيهم يكونوا in V1, they should be in V2. إذا بجي لعند this node, it's connected to elements in V2 بس not connected على ولا شيء ب V1, so I will put it in V1 also. In this way, I partitioned my graph into V1 and V2 such that there is no vertices, edges in the same set, and the only edges اللي معقول نشوفهم are between the two sets, V1 and V2. Okay. Another of bipartite graph was coloring the graphs. So إذا you look on لونت what is in V1 in one color and V2 in another color. Basically, the idea of coloring comes from if you can color a graph in a way such that no two adjacent vertices have the same color, then this graph is bipartite. لأنه the same color حتحطوهم ب V1 و the other color بتحطوها ب V2 وبما أنه no two adjacent vertices have the same color, then adjacent حيكونوا كل وحدة بست. So if هيدي adjacent على this one حتكون ب V1 والثاني حتكون ب V2. So هي another way to look at bipartite graphs. هلا شو عم يطلبوا منا؟ عم بيقولوا لنا بال first question if G is a bipartite graph that can be partitioned into V1 and V2, we need to show that the summation of degrees in V1 is equal to the summation of degrees of vertices in V2. Okay, first, what is the degree of a node? If I have a node, then the degree of it is the number of edges that are connected or that are going out منه. So إذا بطلع بهيدي النود, I have like 3 connections. The degree is 2. What I'm saying is, okay, بعد ما حطيت my elements in V1 and V2, the sum of degrees in V1 is equal to the sum of degrees in V2. يعني degree of A plus degree of D plus degree of F is equal to degree of E plus degree of C plus of B plus of G in this case, okay? This is what I want to prove. And if you take a moment to think about it, well, the degree represents the number of vertices, the edges that are coming out from a node. And what is specific about bipartite graph is that any edge is a common edge between V1 and V2. It's an edge that connects V1, a node in V1 to a node in V2. So any edge is basically adding a 1 to the summation of the degrees in V1, but also adding a 1 to the summation of degrees in V2. So there is like a kind of balance between the degrees. Okay, if I look at every edge لحالها, this edge will give me a +1 here, but also a +1 in the other. So from this idea comes the proof. Given a graph that is bipartite, this is V1 and this is V2. Let's color them. Let's say whole in blue. Let's keep Holike in red. The idea of the proof is pretty simple. Take each edge. We take each edge E. Each edge E connects exactly a vertex in V1 and a vertex in V2. معناتها of I can add عليه a +1. The degree in V2 I can add عليه a +1 and what is this one? So each edge contributes exactly 1 to the first sum and exactly a +1 to the second one. وإذا كل ما عم روح بالedges I add a +1 على both counts, basically I will end up with the same sum على اليمين وعلى الشمال. So if I look at this edge, it's giving me a +1 هون, but also a +1 here. If I look على this edge, it's giving me a +1 هون, but a +1 here. This one is a +1 هون, and a +1 هون. And this one is a +1 هون, +1 هون. As I sum them, it's a 4 by 4 in both cases. So therefore, the total number of edge points in V1 is equal to the total number in V2. The proof is pretty simple. For part B, okay, part B is interesting. In part B, they're telling us that we know that if G is a bipartite graph, then it has all cycles should have even length, okay? And in this part, we need to prove the converse. So if a graph has, إذا عندي a graph with no odd length cycles, then it is bipartite, okay? Let's try to understand ليش a graph that is bipartite shouldn't have an odd length cycle. Let's take the simplest example. For example, 3 for the odd and 4 for the even. Okay? And if it's not a cycle, then it's easy to prove. So if we have an even cycle, it's easy to alternate. I start by a color, then اللي حدا it's a different color, واللي حدا it will be the alternative color and the different color. So I end up with these two being in V1 and these two in V2. And why بدنا نعمل هيدا الشيء؟ إذا بنفرشه للجراف like we look عليه هيك إنه بنقص السايكل at some point. Let's keep in mind إنه هيدا السايكل. Let's denote them by هيك. إذا I know إنه it's even length, then أكيد the index of the first element is even, with the index of the first element is odd. Oh, it's easy to say لأنه إذا I have uneven, then رجعت على an odd length. Okay? So basically, بما إنه it's even length, the first index that is even, the last one will be odd. وby alternating, it's like saying كل اللي على even let's color them ب one color, وكل اللي على odd let's color them بالcolor الثانية. So it follows naturally إنه the end point على اليمين وال end point على الشمال حيكونوا ب two different colors. So even if في هالconnection بيناتهم that is the cycle ما حتتأثر لأنه already هن ملونين ب two different colors. أما إذا طلعنا بال odd length cycle, then كيف ما جربنا نلونه, let's start home by pink, then let's take another color, yellow, then بجي لهون. I can't color this by yellow لأنه it's connected على واحدة in yellow, so I keep it red. I color this by yellow كرمال اللي قبلها كانت red, بس then I have two elements with the same color that are adjacent. And I can see it كمان easily إذا فتح الجراف in the same way مثل قبل. It's 0, 1, 2. بما إنه it's a node length cycle, then the index of the first and last element قبل الcycle حيكونوا the same parity. So إذا عم قول لونه كل عملوا alternation, so كل الأرض حيكونوا باللون الثاني. الاليمنتس اللي هن على same color. So من هون بتجي the idea إنه if it is a node length cycle, it cannot be bipartite. هلا بدنا نقول إنه if إذا ما cycle, it is على أكيد a bipartite graph. Okay. So إذا we want to prove هيك شيء, basically let's look at the base case of our problem. يعني أكتر شيء ما قلته simple إذا مثلا we have this kind of base case where I have only one edge, which is no odd cycle. Okay, so if I have this base case, well, the claim holds trivially. Since, well, we have no cycles, it's only one edge, so there is no cycles in this mini graph. And it is bipartite. لأنه if I have only two nodes, then put one in V1 and the other in V2. So my claim that because it has a no odd length cycle, then it is bipartite, holds على هذا الشيء. إنه it has no odd cycles and it is bipartite. هلا we need to prove it على a graph with m vertices, m edges. Okay, so let's put our induction hypothesis, and let's assume that all graphs with m minus 1 edges are bipartite if they have no odd length cycles. Okay, so I assumed إنه all the graphs with m minus 1 edges that are bipartite أكيد ما عندهم odd length cycles. و if it's not an odd length cycle, إذا ما عندها an odd length cycle, then it is bipartite. هذه my assumption. Okay, so I assumed إنه all graphs with no odd length cycles و m minus 1 edges are bipartite. Okay, let's build my real graph G that has m edges and doesn't have an odd length cycle. Okay, I started by a graph G that has m edges. There is no odd length cycle بقلبه. Let's look at my inductive step. Usually اللي بنعمله in that cases, since عم أعمل induction على ال edges, I look at one edge in my graph and I remove it. I try to check شو صار عندي بالجراف اللي كان موجود قبل. So what I did is removing an edge. So now my graph G prime, that is the initial graph, بس شلت منه this edge. Okay, now it's with m minus 1 edges. لأن initially I had m edges. بس كمان it is it has no odd length cycles for one reason. إذا a graph initially let's say ما عنده odd length cycles so it's differently اوكي هيدا مثلا ما عنده odd length cycles اوكي إذا بيجي I remove one edge then I cannot create an odd length cycle okay it should be clear so my smaller graph has m-1 edges and no odd length cycle then by my assumption it is bipartite okay this is what I assumed every graph with m-1 edges with no odd length cycles is bipartite are bipartite okay so this graph is bipartite it means I can partition this graph into two sets v1 and v2 such that there is no edges in the same set and all the edges are from a set to another okay so I divided my graph v g prime that is v the same number the same vertices ما تغيروا أنا I removed بس an edge into v1 prime and v2 prime let's call them v1 prime and v2 prime such that they follow the condition تبع bipartite graph okay هلا we want to I need to insert again this edge اللي طيرتها من my graph بدي ارجع احطها let's try to build v1 and v2 for the bigger graph g from these two v1 prime v2 prime okay and let's look at trivial cases like the other example before so if I have a trivial case like E is an edge that أصلا goes from v1 prime to v2 prime so all what I have to do is basically to add this edge to my graph and keep the nodes مثل ما كانوا the same configuration and add this edge E. What I have now is the same v1 prime v2 prime for the graph G. There is no connections edges in the same set all the edges goes between v1 prime and v2 prime it covers all the graph G so G is bipartite. This is for the trivial case. Let's look at a more interesting one. Let's say now this is v1 again this is v2 I have the nodes I have the connections some way or another and let's say that this edge E is initially connecting two nodes UV that حطيتهم ب v1 prime أو ب v2 prime let's say without loss of generality in v1 prime if it is in v2 prime then it's a symmetric case I do the same okay so let's say this connection doesn't go between the two sets instead it's in the same set it connects nodes that are in the same set okay هلا we can't keep v1 prime and v2 prime in this way we need to rearrange them بطريقة إنه this edge E should go between the two new sets v1 and v2 but let's try to build these two v1 and v2 okay the key insight here is that UV can't have a path in G prime. Why? Because any path between U and V, okay, so if this is U and this is V, any path between them without looking at E should be by لأنه I'm أشتغل in G prime, so I don't have E هلا. I can't go from U to V in the same set. I should go to V2 go back okay let's say عملتها بس مرة يعني رحت وجديد then it is an even path صح let's say إنه هيدي الروحة والرجعة ما دغري أخذتني عند V. So اضطريت أعمل an alternation. هيدي the first even بعدين another even. So كل روحة رجعة to get to V will give me a two length. Okay, length of 2. If I add them, then any path between U and V should be of even length. Okay, if there is an even path يعني هيدي U there is a path from U to V and G prime that is even. Okay, يعني it is 2m plus, let's say 2n plus 1, or let's say it's 2k plus 1. In the graph J في عندي كمان the connection from V to U. What did I get here? I got a cycle that is odd because it's even plus 1. So 2k plus 1 plus 1, it's 2k plus 2, which is 2 into k plus 1, which is even, which is the sorry. Okay, it's even, so it's 2k, 2k plus 1, which is odd. Okay, so I got a cycle that is odd, but my assumption when starting was that J has no odd cycles. So there can't be a path from U to V. This is الشيء اللي قدرنا نستنتجه إنه in the graph G prime ما في a path بين U and V, and the only path between U and V is by putting this edge E. Okay, this means in the bigger graph, if I don't have E, then what I have now is two disjoint components where U is here and V is here. Now, if it's not disjoint, then there should be a connection between U and V at some point. But since there is no connection between U and V, okay, I can partition my graph into two sets A and B, where U belongs to A and V belongs to B. وهنا the two disconnected components اللي فصلوا U عن V. Okay, so by disconnecting these two nodes, what to do? Let's try هلا to. So شو صار عندي initially V1 prime وعندي V2 prime. I have A and I have V. Okay, A and V are disconnected components. V1 prime and V2 prime بعدهم like before, two sets that are disjoint. So what I will do is flipping around the elements. I will basically check what is the connection between V1 prime, the intersection between V1 prime and A, and I will take it. And what is the intersection between V2 prime and B, and I will take it. And these two will form my V1. So my V1 is V1 prime intersection A, union V2 prime intersection B. Okay? These two are there is no edge between them. لأنه initially A and B are disconnected. V1 prime and V2 prime are by construction without the E. ما في, there is no the connection بيناتهم. So I can put them all in V1. Okay, and for V2 I will do the same. So by taking the intersection with A and B, basically I'm not taking any connection that is from here till here. Okay, لأنه إذا برجع بطلع ب U and V, basically I'm saying ما في this path, so there's nothing طالع من U that connects it to V. Okay, so what should be done is putting V in the other parts from the graph. So this is done by simply looking at where V1 prime intersects with A and where V2 prime intersects with B بحطهم be the same set. And also look at where V1 intersects with B and where V2 intersects with B with A وبحطهم be the same set. And by this عملت a partition for my graph. It's basically the partition of the graph G, the bigger graph, into two sets V1 and V2 that are disjoint. فيهم كل ال vertices و the edges are only between V1 and V2 by the construction لأنه A and B are components that are disconnected. Okay, so طلعت من a graph that has a node length cycle that has no odd length cycle وصلت a partition of the graph. So basically this is proving any graph with no odd length cycle is bipartite. We already know every bipartite has no odd length cycle, so cite if and only if statement. Okay? Okay. Okay, so let's solve this problem. In this one, it's focusing on planar graphs and the Euler formula. Okay, so what is أول شيء in this problem by a graph من a connected and undirected graph without self. So each time being the word graph, it's a connected undirected one and it has no loops. Okay, a graph is called planar if it can be drawn in a way in a plane such that you don't have edge crossings. Okay, so the only way two edges can intersect is and nodes. Okay, so let's take this example. Well, these edges كيف ما رسمت الجراف I can't remove these intersections. So I can't get a planar graph this one. Unlike this one, let's say this edge كنت رسمتها هون صح it's crossing هون بس I can remove it من هون وارسمها من برا, then I will get a planar graph. Okay? A planar graph is defined by also the number of faces اللي عنده إياهم. So as we look at the first example, well, it's clear that we have like 1, 2, 3, and 4 faces. But why is it the case that okay, we call each region a face, but why is the exterior also a face? Okay, let's try to look at Euler graphs and planar graphs in another way. Okay, let's instead of looking at a plane, an infinite plane, let's start to fold this plane into a sphere. And when folding this plane into a sphere, what I have now is this part of the sphere is my graph, and the exterior that has no limits, well, it has nothing special on a sphere. It's like any other face. So any exterior on a plane is like any other face on a sphere, and that's why it's a face. So this is face 1. This would be face 2. Okay. This is the definition of planar graph. هلا شو طالبين منا؟ Basically, they define a formula for planar graphs, the Euler formula. Okay, that states the number of vertices n minus the number of edges n plus the number of faces is equal to 2. Okay, and well, if I'm saying it's equal to 2, يعني عم نقول any planar graphs. Okay, if I إذا بعمل n minus m I add عليها the number of faces, I will always get to it's an invariant characteristic of planar graphs. Okay, under any planar deformations of such a graph, I remove an edge, if I add an edge, well, the formula is capturing a properties of these graphs, so it remains already the same. Okay. So let's start our proof like by taking the base case. Let's look at a tree. Okay, and for a tree that is an undirected graph with no cycles, well, it's no cycles, so it's the number of faces are 1. Okay, why trees are like good base case? Okay, well, trees have like a special property where the number of edges is equal to the number of nodes minus 1, and the number of faces is equal to 1. So whatever is like we always have n minus n plus f is equal to n minus n plus 1 plus 1, which is equal to 2 by simply replacing n by n minus 1 and f by plus 1. Okay, so whatever is the number of nodes, whatever is the number of edges in a tree, and the faces are always 1, I will get the n value that I have. Okay, so this is my base case. For a tree that is a planar graph, I always have n minus n plus f is equal to 2. And now we need to continue this proof by the inductive step. Well, we need to prove like for f faces, it's true. This is what we need to prove, that for f faces it's true, assuming for a graph with f minus 1 faces, it was true. Okay, and to go from f faces to f minus 1 faces, I can simply like merge two faces into one, and by merging two faces into one, I simply mean removing an edge. How? Well, let's look at one example. It has 1, 2, 3 faces. If I remove this edge, I merge these two faces مع بعضهم, I will get this, which is 1 and 2. Okay, so by removing this edge, اللي صار انه بعمل a planar graph بس that has the number of faces initial minus 1. Okay, let's go هلا عندي n prime, n prime, f prime, initially I had n and f. Okay, so شو اللي صار بالn والm والf after removing this edge? Well, the number of nodes بعده the same. Okay, so n prime بعرف n لأنه ما دقرت بالنص. والm prime تغير. m was m minus 1. And the number of faces also added by 1. So both decreases by 1. Okay. هلا أنا عم أقول إنه it holds. هلا صار عندي a planar graph with f minus 1 faces. By my induction hypothesis, I know إنه n prime minus n prime plus f prime is equal to 2. هيدا by the assumption اللي already عملتها. Okay, so n prime minus n prime plus f prime equal to 2. But what is n prime minus n prime plus f prime? I need to link it to n, m, and f to be able to get info about the initial gravity that was with f faces. Okay, so n prime is the same as n, but m prime is m minus 1, and f prime is f minus 1. هذا equal to 2. Well, n minus m plus 1 minus 1 be 0, it's n minus m plus f, which is equal to 2. Okay, so starting by an f minus 1 faces where the property holds, وصلت على f faces where the property still holds, so the proof is basically done. It's done by induction. Okay. This is an interesting problem. Okay, let's go to this problem. It's a DP application. And in this problem, we are looking. Okay, so basically, we are given n tasks, T1 till Tn, and each task Ti is represented as a start time, a finish time, and a profit. Okay, so I have a list of tasks. Each task will start at time s and will end at time t, at time f. Or I can get some profit from this task. Okay, I need to like choose tasks أكيد that doesn't overlap and I can't multitask, okay? So I need to choose tasks that are not overlap. يعني whenever I'm doing one, I can't do another one in parallel, okay? So whenever I start a task, until I wait until it ends to be able to start the other task, okay? I need to choose such tasks in order to maximize my profit. So we need to select tasks that maximize the profit, but doesn't overlap, okay? So, well, think about it. You know, why can't we just do it in a greedy way? Like, why can't we pick the tasks with high profit? خلاص, we skip overlap. And I start by the highest profit possible. I take it. Well, there is an overlap. I skip. Another highest profit. I take it. Well, if I do it this way, I may select a task that is okay, the high profit. But I might also block as well a time period اللي هي time period تبع this task where كان فيني مثلا اخذ for example 2 medium profit tasks that sums to more يعني for example look at this. Well, what I have is مثلا a task T1 with a profit of 10 and let's say this is the highest profit I can get. I have 2 tasks كمان. Okay, let's call it T2 عندها a profit of 4. Let's call it T3 عندها a profit of let's say 8. Let's say هيدا time يعني هيدا start time هيدا finish time start finish. Well, the greedy approach would say إن okay خذوا هيدا. Well, أخذت هيدا صار عندي a profit of 10. بس هلا I can't take this one ولا take this one. بس let's say ما مشيت greedy وما أخذت the 10 وأخذت both the 4 and the 8. Well, I get a 12 which is bigger than 10. So this is a counter example now. A greedy approach doesn't work. Okay, so we can't work with a greedy approach. Instead, we will be like trying to find the tasks that maximizes my profit. Okay. So let's take an example. Let's start, for example, let's take a task 1 and a profit of 6 a time from 2 to 6. Let's say task 2 and a profit of 5 time 1 to 4. Let's say task 3 and a profit of 8 time 3 till 8. Let's say task 4 and a profit of 3 time 5 till 7. Okay, so let's put them on like a timeline to be able to see them better. So I need 1, 2, 3, 4, 5, 6, 7, and 8. Okay, for task 1, it's from 2 till 6, so till there. Okay, this is task 1. For task 2, it's from 1 till 4. This is task 2. For task 3, it's 3 till 8. Well, 3 till 8. This is task 3. And for task 4, it's 5 till 7. This is task 4. Okay, so given this set of tasks, like we need to know which tasks are like fully completed before any given task starts. يعني before task TI starts, what are the tasks اللي بيخلصوا دغري قبل TI? Such that إذا أخذت the task TI, I know what is the set of tasks اللي I can pick منه a task وأخذها مع TI, okay? لأنه إذا I know إنه TI starts at time F وال tasks كلهم finish at time F يلي such that F أصغر من S, then إذا I take TI, I know إنه ال tasks اللي بعد فيني أخذهم هن هول اللي finish time تبعهم is less than S. Okay, so basically I'm like trying to look at the finish time of each task. Okay, so I care about the finish time. Let's keep this in mind. Okay, so for each task let's say for each task I either take this task, I either take it or I skip it, right? Or I skip it. So the P at I is telling me what is the maximum profit if I take the task I, okay? This is what GP at I is telling me. What is the maximum profit up to task, okay? So the maximum profit up to task I would be the maximum between not taking task I at all, okay? Which is skip task I. I can either skip it or take it, so I need the max finally. I'm trying to maximize the profit, okay? it is I take it, I add a profit at I add the profit of this task, but I need to find هلا أي task فيني هلا أخذها، لأنه okay أخذت this task but what task can I take? What task finishes exactly before task I, so that I can take it. It's compatible with the set of tasks I'm building. Okay. So I call it ZP at J, where J is the task, the last task, أبعد task that is compatible with the task that finishes before task I starts. Okay. I can go over all tasks and do it in linear time and check if the finish time is less than the start time of I take this task, otherwise I search again. But well, I'm looking for a number, so I can I have the finish times of my tasks, and I can think about like binary search. But to binary search, I need a sorted set. Okay, so basically, before doing anything, let's sort the finish times. Okay, so in that case, it would be F2, then F1, then F4, then F3, right? You agree? 2 finishes before 1, before 4, before 3, okay? So, I have this array of sorted finish times. I need to find the last number that is less than SR, okay? I can solve this easily by binary search, a normal binary search algorithm. So instead of going linearly over all finish times and find the element that is less than the start of the task I can binary search for it. And this will reduce the time in N and off and the O of log N. Okay? So instead the loop I will have وكل مرة عم أعمل the worst case one binary search to get this one. Okay? Inside I have an O of N log N to sort the finish times. So it's overall O of N log N, which is better than O of N squared. O of N squared will come and instead of doing binary search here, to go over all tasks. Okay? So again, we don't forget the base case. For the base case, it's DP with no tasks, which is basically a profit of if I don't take any task, then I'm not making any profit. Okay, and this is the base case, the time, and the recurrence relationship. And yeah, that's it for today. Well, good luck for your exams, and bye.